Good to go. All right, good afternoon, everyone. Thank you very much for coming to this session. Thank you very much for having me here in Madrid, in Spain. I'm from Canada, so it's a little bit colder where I am right now. But very, very happy to be here in some slightly warmer, maybe tropical weather. Today we're going to be talking about a few different things. The agenda is we're going to give you a little bit of an introduction about what Geotab is as a company. I'm going to talk a little bit about autonomous vehicles, what the future looks like from that perspective and where we are today, how we're using big data to help drive a lot of the advancement in this area, and then lastly, and I think most importantly and most interestingly, what we're doing from a smart city perspective as it relates to a lot of this big data and how we're using it, how we're transforming it, some of the tools that we're using at Geotab. So my hope is that you can take out of this some practical examples of how you might implement some of these different methodologies within your own companies. So first of all, Geotab, we are a world leader in telematics. We're actually the second biggest telematics provider in the entire world, next only to Verizon. So the companies that we range with are commercial vehicles. So we deal with companies in size of one vehicle all the way through to 80,000 vehicles. Big name brands like Pepsi, like UPS, Enterprise Rent-A-Car, Hertz. We've got offices in Toronto, in Las Vegas, and we've also got an office here in Madrid in Spain as well. So very exciting company, a lot of growth happening within the company. The actual device that we have is a small device, plugs into the onboard diagnostic port of the actual vehicle, and it collects a number of different readings from there. So we're able to collect instantaneous speed, GPS. There's an accelerometer built in there as well too, so we can track acceleration in the X, the Y, as well as the Z direction. Really, really granular data. In addition, what makes it really interesting is that we've actually designed it to be really an IoT hub for that commercial vehicle. So you can plug into that device just about any other sensor. So we've got people using it to track weigh scales in garbage trucks. We've got people using it to track temperature in the back of reefer units as they're delivering food to, say, a McDonald's or a Subway. And it all comes through one stream, which is really important. So you can collect trip data, engine status data. We've got one of the richest engine status data sets in the entire world. I'm tracking everything from engine RPMs through to seatbelt buckled, unbuckled. So some really, really rich data here. That IoT device for the vehicle is something that is, I think, will enable us as an organization and as a provider of a lot of this open data to even go further in the world. So I thought I'd first take a quick look at, what does that future look like? What does that future of tomorrow look like with autonomous cars? We're almost there in some respects and very, very far in other respects. So that world of tomorrow, what does it look like when you've got a completely autonomous level 5 car? People won't own their own cars. They may own their own pods that attach to a vehicle or a car or something like that. There might not be a driver's license. Right? Why do you need a driver's license anymore? Maybe no headlights, stoplights, or signs, because these vehicles can operate autonomously and irregardless of light. Fewer cars on the road, so that means less maintenance and wear and tear on all of our roads for our smart cities. No driveways or garages. Here's an interesting one: nobody drinking under the influence while driving. That may be great. What does that mean for everybody else, for the entire ecosystem? That means, well, you know what? You might have alcohol sales being boosted in restaurants as a result of that. Here's an interesting one as well, too. So premium child transport systems. As a father, I'm not sure how much I would trust that, but can you imagine sending your kid to daycare or to school in an automated vehicle and having them return at the end of the day? Cities may lose money from traffic tickets. Lawsuits, interestingly enough, may be between big companies now instead of between people, because who's to say what's going to happen with the decision that these autonomous vehicles are making using the AI Is the battle going to be between, a Ford and a GM as opposed to between Mike and Andrew, right? So really interesting. And drones may make that last leap of faith in a delivery. If I'm a UPS vehicle or an Amazon vehicle, I may have a drone that just makes that last delivery. So some really interesting things to think about when we think about the future of autonomy and autonomous driving. But we're not there yet. If anybody's seen this picture, it's kind of funny. What they did is this was, I think, from last year. They had a car, an autonomous driving vehicle, and they used a flour bag and kind of sprinkled flour around the car with laneways, and it trapped the autonomous vehicle. It couldn't figure its way out. So all these cool things, but we're still a little bit a way off. In fact, right now, the average age of vehicles on the road in the U.S. is 11.6 years. So even if we had the technology of today, it's still going to take us a number of years to get to where we need to be. So it's really an aftermarket problem, I think, at the end of the day. And it's going to take a complete ecosystem approach to bring all of this to fruition, a complete ecosystem approach. So from the sensors that you're dealing with, the LiDAR sensors, radar sensors, camera systems, and of course, telemetry systems. It's not just one of these sensors or one of these ways that's going to make it happen. It's going to be a combination of everything working together in an ecosystem. You're going to need to have vehicle-to-vehicle communication, vehicle-to-infrastructure communication, and vehicle-to-cloud communication as well. The entire ecosystem is really required. And here's an example of why, right? You've got a car driving around a blind rise, maybe in the middle of absolutely nowhere. How does it really know that there's an accident down the road? I need that vehicle-to-cloud communication to be able to get access to that data, right? And it's needs to be something that's really ubiquitous. You need an open ecosystem, a lot of flowing data from a number of different vendors. You need to build out your systems in an open fashion so that this data can be had, so that if I'm vehicle A over here, I know that there's that accident up around the corner before it comes. So we really believe in GeoTap, in an open platform, open design for everything. So all of our APIs, you could develop our entire platform off of the APIs that we actually push out there. We believe that the data is the customers. So if I'm a fleet and I'm a customer of GeoTaps, I have full access to all of that data, all through the APIs, streaming live in real time. And we believe that creating that closed loop infrastructure, that really stifles imagination. It stifles creativity. It stifles innovation. And it's not something that really should be done. We should be working in this really open world where the data is flowing. And what we're finding happening, we see a lot of data islands and data silos being created. What we're doing is we're creating everything in a nice giant data lake so that we can do a lot of rich analysis, rich AI, rich machine learning from this data. But in order to do that, you have to start with quality data, high quality data. And for us, I think the key to success has been in our curve-based logic that we apply. So we don't sample every second or every 2 seconds or every minute. We sample only the most important points along the curve that matter so that we can reconstruct what actually happened in real life. And I'll tell you why that's important. If you're sampling in a time-based interval, you're going to miss something along the way. You're going to miss, in the case on the upper left there, that turn is going to be completely missed. You're going to cut a diagonal across the road. The case in the bottom here, we're looking at speed versus time. You're going to miss that upper point. We sample the most important points and make sure that everything in between is interpolated. So what that does is a number of things. It allows us to send fewer points to the cloud, but then we can reverse interpolate that at the end of the day. So this is how we've set up our infrastructure here at GeoTaps. I thought I'd give you a kind of a quick rundown. So we're dealing with about 900,000 vehicles right now across the world, scheduled to be just over 1 million in January. So very, very fast growing. About, just under 2 years ago, we were at about 400,000. So a rapidly growing company here. From each of the vehicles, it operates off of a cellular network, and we send all the data through to our gateway servers. So we have a number of different gateway servers that process the data. And then we send it to a production cluster for, if I'm a customer, I have access to what we call our My GeoTab system, which is our production system. You can go online, check out a whole series of trips that you've made as a customer, set up different rules and thresholds within your database. So that's kind of on the production side. The side that I deal with is really on the big data side. And that's where we're talking about the big data streaming here. So from those gateway servers, we actually have, we've set up Kubernetes in an orchestration fashion such that we have Dockerized containers in there that will be spun up, and then we send the data using streaming inserts to BigQuery. And so the delay from it being recorded on the device through to the time it's actually available to do some analysis in BigQuery is about 5 to 10 seconds. And of course, to our production cluster in near real time. We do approximately 2 billion raw data points a day, and that's using our curve-based logic. If we were to extrapolate that out and look at real-time-based sampling, we're looking at about 20 billion points on a daily basis that we do. So it's a lot of data. What I thought I'd do is I'd talk to you a little bit about some of the tools that we use at GeoTaps. So this kind of talks to our stack a little bit. And the reason that we chose BigQuery first and foremost was we had a lot of engineers with some really strong SQL experience. And Google BigQuery lends itself very well to that kind of thing. So we use standard SQL and not legacy SQL. It's easier for those guys to just jump into BigQuery and run some queries and be very effective very quickly. It's very, very fast over large data sets, like within seconds. It's incredible. It never ceases to amaze me, the speeds that BigQuery operates. From a data processing perspective, we use, as I mentioned, Kubernetes for some orchestration, sending data through to from our gateway servers all the way through to BigQuery through streaming inserts. We also use, just recently, Airflow. And I was in a talk yesterday by the Spotify lady, and it was fantastic. She was talking about data quality and how you monitor your data coming into your system. And that's what we're using Airflow for right now. So we're setting up all of our jobs in Airflow through directed acyclic graphs, and we're monitoring them each step of the way to look for job failures. There's a lot more that we can do right now. So what we're looking at doing is ensuring that the metrics that we're anticipating for a lot of our big data analysis are remaining consistent from an hour-to-hour basis, day-to-day, week-to-week. So Airflow has been really invaluable for us. We use IPython or Jupyter notebooks across the board in multi-departments. So we've got big data champions in different departments, and our big data team really leads the way and showcases what you can do with this data. That's been invaluable for the entire ecosystem as well too. We use, of course, pandas for all the data manipulation. And from a machine learning perspective, we use both TensorFlow and scikit-learn. It's easier for our developers to get into to scikit-learn, of course, but TensorFlow has been really strong for us. We've done some incredible things combined with Google as well too. We had Google come in for a full week session to do some machine learning training with our staff. That was an invaluable exercise. I'll talk about a few of the things that we're doing from a machine learning perspective. So two things come to mind right off the bat. So predictive analysis is important in the world that we live in. So is your battery going to fail in your vehicle? Are your brakes going to fail? Is your transmission going to fail? So the different cues that we have in the data, for instance, from a battery perspective, we're able to look at the cranking voltage in the car's battery and be able to tell if it's strong, weak, if it's going to fail. And we use machine learning algorithms for that. Another mechanism, another way that we're using machine learning right now is, I think I'm missing a slide there, but is for vehicle classification. So vehicle classification, what we do is we look at the driving pattern of a vehicle. And to be able to benchmark anything in our world, it's important for us to know how a vehicle is driving. Am I driving like a pizza delivery model? Am I driving like an office worker? Am I driving like a scheduled delivery type vehicle? So what we do is we use machine learning, and we've developed different features that allow us to predict what those driving patterns will be like. And I think for us, the biggest challenge was in the feature engineering, understanding, what features it was going to take for us to be able to derive some insight out of this data. One feature that I wanted to show you there was on the x-axis, we had the day of the week, and the y-axis, we had the hour of the day. And over a 6-month period, we just did a massive plot of where all of those, the activity for those vehicles was being lined up. So if you were looking at an office vehicle, you would see, a big line on the 9 to 10 a.m. in the morning, and then another big line maybe 5, 6 at night when the vehicle is coming home. If you're looking at a school bus type orientation, you might see that same thing, but a little bit elongated. Now, these are very simplistic features, but we designed a lot more into that as well, too. So that's been an interesting way that we've been using TensorFlow and machine learning. So, while big data is crucial for all of these advanced driver assistance systems, there's also a massive play in the smart city realm. And that, for me, is really, really interesting. There's a lot of socioeconomic impact that can be had by all this data at mass. Traditionally, as a company, we were a telematics company providing services to end customers. We still do that, but data is the future for us. That's where we see things going. So what can we do while still protecting the privacy of our end customers with this massive volume of data that we're sitting on? And the answer really is in a lot of the smart city solutions that we're pushing out. So like I said, we've got just over 2 billion raw data points that we collect a day. Only a third of that is traditional telemetry data. The rest is, are my windshield wipers on or off? What's the ambient air temperature? How far have I pressed the pedal, for the gas? What are the engine RPMs? Is my seatbelt buckled, unbuckled? So there's that data that is just so rich. And we've got blanket coverage in North America and about 100 countries across the world right now. Like I said, about 900,000 vehicles. And the real play is in the smart city realm. So this is another slide that didn't quite get updated. This is supposed to be a time lapse showing traffic flow from in Washington, D.C. from 12 a.m. all the way through to midnight the next day. Really interesting to see it kind of animate and move. And one of the things that we're doing with all of this data, the data that can be aggregated, is we're providing it for free to municipalities through free data access licenses. So what I encourage the rest of you to do in this room is if you see an interest or a need for any of this data within your applications, please feel free to reach out to us. We're launching a new site, data.geotab.com, by the end of the year. And as I'm showing you some of these slides here and what we're going to be launching, think about it and see if you can actually use it within your municipality, within your city, within your business, okay? One of the things that we're pushing out is hazardous driving areas. So we look at that and we look at within a specific area, how many times are people slamming on the brakes? How many times are there these near accident collisions? It's very easy for a municipality to see where collisions have happened in the past. Where are those near misses? Where are they happening? What we see happening here, if we look at the bottom left of the screen, this is in Oakville, where we are, just outside of Toronto. There's a very busy road, and you have to turn left to get out of a lot of these driveways here. And a number of times, you're just seeing these near accidents. And since we did this, we found it interesting that the city actually put up traffic lights in a few areas, unbeknownst to us. So we thought that was a kind of an interesting validation for the data that we're pushing out there. Similar here, this one's in Austin, Texas, at the top in the little bubble there. Very dangerous intersection. There's a blind rise. And normally there's a sign there that tells people about that blind intersection. But there was some construction that happened, and the sign got taken down. So we saw a significant increase in that area just as a result of that. Cellular dark spots. So we actually can obviously track the cell signals, carrier independent, and we can look at where there are troubles within cities from a communication perspective. And why this is important is if you're designing a city, a connected city for tomorrow, you need to understand where your coverage is great and where it isn't. So these are looking at dark spots over a period of a month that have been very, very persistent. We also look at inconsistencies and time fluctuations as well too. So while these are the persistent ones, which happen all along kind of the M50, kind of near to Cañada del Real and near Villa de Vallecas, pardon my Spanish, I don't think I've got those quite right. But you can kind of see where some of the areas are a little bit poor and where you've got good coverage in general, but there are some inconsistencies. And again, this is looking at only the persistent issues. Hyperlocal weather conditions. This one's really neat, and a lot of people don't really think about this when they're thinking about telematics at first. So we've actually got the capacity to look at, from about a third of our vehicles, the ambient air temperature. So we can track hyperlocal, what is the precise temperature, just by looking at these vehicles as they're driving around the city. And this is for the city of Toronto where we are, and you can see it kind of light up in different parts throughout the course of the day. And why this is important, because there's areas of the city sometimes that are a little bit hotter than usual, either due to a number of emissions, a number of vehicles circulating in the area. It might just be the building architecture in that area. And it informs the city so that they can implement different mitigation strategies, such as, green roofs. I see a lot of green roofs over here in Madrid as I've been kind of looking around to help with the temperature mediation. So that's an interesting use case. What we're actually going to be doing too is we'll be pushing out one for hyperlocal precipitation as well. So looking at windshield wipers when they go off and on, and can I tell, is it raining over here? That is very difficult for weather companies to do. They can tell you with some degree of certainty where it might be raining, but now you've got ground truth all across the globe, right? So it's some really interesting stuff that goes beyond the traditional telematics field as you're designing these smart cities. Road impediment data. As I mentioned, we've got that accelerometer that's sitting in the actual vehicle on the OBD port. We track in the Z direction as well too, right? So we track not only where there may be a pothole, but how frequently are people going over that pothole? What is the magnitude with which that pothole is causing disturbances? Can I then look at an entire road and send a crew out to fix the worst roads in my city? One interesting thing is that some of the municipalities we're working with, they send crews out 3 days a week just to monitor and check the road conditions. If we've got, say, 80% coverage in a city, why not focus your crews to spend half a day maybe looking at that 20% where we don't have good coverage? The big idea behind all of this is, as you're developing these smart city solutions, you're putting in place a lot of complex infrastructure, very costly as well too. Why not leverage the power of what's happening already in your city? If you've got thousands of vehicles driving around that are telling you something about your city, why not benefit from that? Intersection intelligence is kind of another neat one, looking at wait times and volume distribution across the board. And not only can we tell you, the wait times within an area, but then we can classify it by the type of vehicle as well too. Again, this is all data that is going to be made available for free through a data access license. So keep this in mind as you're thinking about potential solutions that you may want to build on top of some of these data sets, right? So we can tell you, if you look over here, there's obviously a lot of noise in the intersection. We've implemented a lot of clustering algorithms through k-means to separate a lot of that noise and then showcase specifically where people are having issues with wait times. You can see across the top there's a longer stretch. That means that people are waiting for a longer period of time within that area as opposed to the narrower stretches. And the image on the top right there is a bit more of a cleaned up version for the intersection. But again, a lot of work is done on removing that noise. And we can look at direction of travel, traffic flow, all sorts of things. Searching for parking. Searching for parking in the city is kind of interesting because it causes congestion, right? Causes frustration. So what we've done is we've identified those areas using geohashes. We use geohashes a lot. If anybody has not used a geohash to do any analysis, it's amazing. You can do some really cool joins. Being in the industry for a while, it wasn't until just a couple of years ago that I even heard of geohash, and I've been working with long lats for a while. But geohashes is really interesting because it divides up the world into a number of different quadrants, and you can look at those quadrants very, very, very narrowly or very large as well too. So we look at specific geohashes and where you actually end up parking. How many times did you kind of circle around? How long did it take you to find that parking spot? And we develop index scores as well too to tell you, what percentage of time in a city do people actually spend looking for parking. We found out that of our data set, New York kind of topped the list there for an average time to park of nearly 8 minutes. Here was an interesting kind of quadrant plot of that same set of data there. The size of the circle indicates the number of people in the city that are looking for parking spots, that are searching for parking. The x-axis indicates the average percent of people that are searching for parking in the city. And then the y-axis indicates the average amount of time that they spent looking for a parking spot. Again, all available through when we release data.geotab.com. Engine idling in the city. So we can tell you, where all the emissions are being generated within a city. We're actually working with the Environmental Defense Fund as well too. And the idea is what we'd like to do is run a pilot where we equip the vehicles with air quality sensors. So not only do you map out emissions through congestion and through engine idling, but you can map out air quality within a city as well too. So that, again, that's through that capacity to daisy chain multiple add-ons into that one GeoTab connected device. This one's kind of interesting because it gives you a macro scale feel for your actual city, the commercial vehicle point of origin, right? Where are vehicles coming from to get into your city? Where are they leaving to out of your city? And not only like the actual vehicle movement, but what types of vehicles? Are they class 7 and 8 heavy-duty trucks? Are they pickup trucks? Are they, multi-passenger vehicles, SUVs? So we distribute it, and we give you a good aggregation of that. So it gives you a good feel as you're designing the routes into and out of your city. I thought I'd throw in a few fun ones at the end. So we did an analysis looking at Hurricane Harvey, of course in Houston back in late August, early September. And we looked at a week before. And a week before, you can see the massive amount of movement of commercial vehicles in Houston. The week after, you can see where it's just 88% reduction we noticed in commercial fleet activity within Houston. And you can see the roadways are kind of cut off because of a lot of the flooding that occurred. So that was kind of just an interesting way of showcasing how big data can be used within the fleet world outside of the traditional ways. This one was really cool too. I was expecting to see a higher jump in magnitude in the z-axis from each of our vehicles when the earthquake went off. But what had actually happened, it wasn't the magnitude, it was the sheer volume of vehicles we had in the area that woke up. So we had a bunch of vehicles just sitting in there, and all of a sudden, at the exact same time as that earthquake hit, all the vehicles woke up. So what I'd be interested in looking at, are there ways that we can build this into early detection systems to, advance what's already been done in the area? So again, an interesting way of using vehicle data to augment what people are doing from a smart cities approach. And this would come in the form of, disaster management. So all of this will be, these data sets will be coming by the end of the year. We'll be making an announcement. It'll be in beta at first. I think we're going to do a full launch mid-next year. It'll be on data.geotab.com. And you'll have access to all of these data sets in Google BigQuery. We'll have a full-on white paper describing how you can actually use the data, sample code snippets in Python so that you can access the data, sample SQL queries. Again, we're a very open company. We believe that in creating this ecosystem approach, we're going to uncover how people can use the data and where there's best value for these smart cities. I mean, we're sitting on all of it already. Let's put it to use. Again, within the actual data.geotab.com, you'll have an outline too of all the fields, what they mean, and how you can use it. So with that, I think that draws everything to a close. Thank you very much, everybody, for having me. Hopefully I was able to share with you some of the insights that we're producing at GeoTab and how that can hopefully be of a benefit to people in the audience as well. Thank you very much.